Welcome to the Nuclear Masterclass. This is, of course, the first time that we run this masterclass online, so a special welcome to all of you. It's great to see that so many of you are tuning in live. We've got more than 1,000 participants, and it looks like about half of you are tuning in live, and also welcome to everyone who is listening to this after the fact. So I look forward to engaging with you a lot over the coming weeks, both this week and over the next 3 weeks, where you will see a lot of different interesting topics ranging from nuclear medicine, nuclear fusion, as well as nuclear astrophysics, where we'll study neutron stars, we'll study how to design proton treatments, and we'll look at how to make fusion energy work here on Earth. And in addition to that, the topic of this week is on exotic nuclei, on binding energy, and how is energy actually stored in the nucleus. So for this, we've got a team joining us today, mostly here from York, where I'm situated, but during the course also from across the UK, as well as from Canada and from as far afield as Australia. So to learn more about this, today we have two speakers. We have Marina Petri here from York and Charles Barton, also from University of York. So Marina and Charles have agreed to come and talk to you. Firstly, I wanted to welcome Marina to the webinar. So welcome to you, Marina. Marina is researching some of the most exotic nuclei in the world. They can only be made in specialized laboratories, and she is investigating how you can use these to study the fundamental aspects of nuclear physics, how nuclei really are put together in us and around us in the world. So thank you so much to you, Marina, for being willing to join us today. Thank you.
It's my pleasure to be here. I hope you can hear me.
Yes, we can hear you. That's good. Thank you so much, Marina. So first, just to get to know you a bit, Marina. So how did you, firstly, how did you get to be here at York?
I came here in York in 2016 when I started the research fellowship with the Royal Society. And before that, I was not in the UK, but I was very keen to work with the Royal Society in advancing the field of nuclear physics. So I was very excited to get this fellowship and be here.
Oh, that's fantastic. Yeah. And so I understood that I think you were actually the first nuclear physicist to get a Royal Society. Is that right?
That's correct. Yes.
Okay. That's fantastic. Thank you so much. So you indicated that you had been a few places before coming to York, it sounded like. So can you elaborate on that? Where were you before York?
Sure. So I'm originally from Greece, and that's where I did my undergraduate degree. That's where I lived my life until the beginning of my 20s. And then I moved around from the UK, where I received my PhD, and then I moved to the States for 4 years. And after the States, I moved to Germany for another 4 years. And I'm happily here to continue my research. But I think this is the typical image that you would have for a scientist that pursues mobility and to grow its international network. So I think this is the life that many of our colleagues actually live and pursue throughout their career.
Okay, thank you very much, Marina. That's great to hear, and I obviously look forward to hearing more about what you're taking out of this, how you use these laboratories to study exciting aspects of nuclear physics. So I think with that, we should move straight into Marina's presentation. Before I do that, just to emphasize that during Marina's talk and after her talk, do feel free, all of you, to ask questions in the Q&A. I can see the questions are already coming in. That's great. So please just bombard us with questions there. I will do my best to field all of those questions to Marina and later on also to Charles. But with that said, over to you, Marina, for your presentation on exotic nuclei on the edge of existence. So thank you so much.
Thank you, Christian, and thank you everybody for joining this masterclass. I'm excited to be here. Unfortunately, we cannot see each other, but we have all the technology here to make it work. And I want to talk about exotic nuclei, not just atomic nuclei, but exotic atomic nuclei. But in order to start and put everything in perspective, I would like to start as a presentation. Is nice to start with a video. And I want to show you a little bit about the scales and give you a feeling of the relevant scales that we are dealing with in nuclear physics. This is a video that I found on the CERN webpage. And this is, if you see here, we will start zooming into a person, and you see here the scales, that's a meter. And if you want to see a hair, you would have to go to the micrometer scale, which is 10 to the minus 6. And this is a diameter for a hair, it's 100 micrometers. And then we need to go deeper into matter, and then you will start seeing terminology from your biology classes. This is cells, and then we are talking about structures of protein fibers at different scales. We are now in the nanometer scale, and we are still talking about biological structures. Nanometer scale, 10 to the minus 9 meters, and we are still at the keratin level. And then we need to zoom further inside, and it's then that we first see a hint of atoms. We are at the picometer scale. And if we want to look at an atom, this is a carbon atom, and you can see the electrons, that's the electron orbits around it. And we are interested about the atomic nucleus. So let's see where the atomic nucleus lies. We are at the picometer scale, and we have to go deeper and deeper and deeper. And this is when we meet the atomic nucleus. This is the object of our study as nuclear physics. What we know, the atomic nucleus consists of protons and neutrons. And if we look at the proton, this is the femtometer scale, 10 to the minus 15. Then we know that the building blocks of everything is quarks. So this is a video, and a very nice video, in order to give you a feeling about the objects that we are working with. And again, showing a cartoon of this. So if we would think of an atom as a sphere, then the radius of the atom would be of the order of 10 to the minus 10 meters. And if we want to look into the atomic nucleus, then we have to go 5 orders of magnitude inside to find the protons and the neutrons, to find the atomic nucleus. Now, what that means, if I want to give an analogy to this, that's an analogy I really like. This is that if you have a basketball and that's your atom, then the atomic nucleus is a grain of sand in the middle of the atom. The interesting thing is that the atomic nucleus actually holds almost all of the mass of the atom. Imagine in this tiny grain of sand that you have almost all of the mass of the atom. That means that the nucleus is a very, very dense object. It's so dense that if we were able to make a dice of 1 millimeter side of pure nuclear matter, that would weigh 200,000 metric tons. What that is, what this number is, this is the weight that a supertanker can carry. Imagine this weight in a dice of a 1 millimeter side. This is very impressive. Now, why do we study the atomic nucleus? So we said it's made out of protons and neutrons. We have been studying the atomic nucleus for many, many years, but it's the most complicated object in the quantum universe. And although we know a lot of things about the atomic nucleus, it's still not clear how the fundamental forces of nature come together in order to build a picture of the atomic nucleus as we observe it in our everyday life. So why am I talking about 4 fundamental forces of nature? I'm sure you know many more than 4 forces. For example, tension, friction, air resistance. So all of the forces are derived from one of these fundamental forces. And for example, tension, friction, and so on, that comes from electromagnetism. And it's 3 out of the 4 fundamental forces that actually are at work in order to build the nuclear landscape. The nuclear landscape is a nuclear physicist's playground. What is the nuclear landscape? Let's take a few minutes to go through the steps that we need in order to build this nuclear landscape. So let's start with something that you know from your chemistry lessons. Let's start from the periodic table of the elements, where you have an arrangement of the chemical elements and you order them by their atomic number, electron configuration, and chemical properties. And let's take, just as an example, beryllium. So the element beryllium has an atomic number of 4, and that means that it has 4 protons, and of course 4 electrons in order to have a neutrally charged atom. But as we are nuclear physicists, we care about protons and neutrons. So I know that beryllium has 4 protons, but then the question is, how many neutrons does its nucleus have? Now, if you look on Earth, and you look at the beryllium that we have here on Earth, which is stable, it does not decay, it's not radioactive, then beryllium has 5 neutrons. And for nuclear physicists, that means that this beryllium is beryllium 9. We simply add the number of protons and neutrons. But then you can ask the question, what happens if I put an extra neutron in the system? Can I make beryllium 10? And the answer is that yes. If you look here, I can make beryllium 10, but now this nucleus has a little bit more neutrons than it wants to have. So it will live for some time, which we will call the lifetime, which is a statistical process, it's an average number, so let's call it a lifetime. It will live as beryllium 10 for some time, and then it will prefer to change into a different element. It will prefer to change its excess neutron into a proton. And this lifetime for beryllium 10 is 1.5 million years. Now, how about adding one more neutron to the system? What do we get? We can make beryllium 11, but that will try to change into a different nucleus after 14 seconds. And we can go on and we can see that if we go to beryllium 12, then that will stay or live as beryllium 12 for 24 milliseconds. And after that, we cannot add any more neutrons to the system. And we can go towards removing the neutrons and see if we can make the system or if the nucleus lives like that for some time or not. And what we have built this way is an isotopic chain. Isotopes are variants of particular chemical elements which differ in neutron numbers. So this is the isotopic chain for beryllium, and I can keep doing the same for every element in the periodic table. And then if I plot what I have in this 2D matrix, here is a proton number going up, and here is the neutron number increasing, then I have the nuclear landscape. And for each element, I will have elements that are stable. These are all the elements that we have here on Earth. They don't decay. Otherwise, we would decay and change into something else. So we have the black circles that are the stable elements. And then we have all their isotopes. And if I color code with this lifetime that I mentioned before, you see that as I go further to the right and to the left of these stable isotopes, the color becomes lighter and lighter, and that means that my nucleus lives for shorter and shorter time before it changes to something else. And that's why they are called exotic nuclei, because they don't live for long, they live for milliseconds, and obviously they don't exist on Earth. So this is our nuclear landscape, and these exotic nuclei is what I'm trying to study. I want to look at properties of these atomic nuclei, of these exotic nuclei. But then you will ask me, but they don't exist on Earth, so why do we want to study these nuclei, right? I mean, if they don't exist here, why do I even care about these nuclei? There is a simple answer to that, and the answer is that these nuclei, although they are very exotic, they play a very important role in the cosmos. And one of the most important and fundamental questions that we can ask as civilization is, what is the origin of the elements? So we know the periodic table of the elements, but where did these elements, where were they created and how? So how are the elements made? And the exotic nuclei play a very important role in answering this question. So if we think of the Big Bang, the elements that we can justify or we can explain is the hydrogen, the helium, and a little bit of lithium. So all of the other elements that make life here on Earth as we know it, they are made in stars. They are made through the birth and the death of stars, through stellar evolution. And there are different mechanisms how each element is made. And why is this very important to answer? We are made of this star stuff. So if we know how they are created, it's as if we are answering questions as how we are created. So this is very important questions. So one of the questions that we still cannot answer, or we are trying to answer, is, for example, if you look at the abundances of each element here on Earth, why is gold so rare to find and therefore it's so expensive? Or silver? And why is iron so abundant, or oxygen? It's the oxygen we breathe. Yet if we want to make something out of platinum for a ring or so, that's very expensive. That's because we don't have a lot of this. And why we have these abundances and how they were created, this is very important to know properties of these exotic nuclei. And I just want to give you a little bit of an example in a video. This is one of the scenarios that we have in mind as to how elements heavier than iron were created in the cosmos. We believe that one of the sites where we can create elements heavier than iron is through supernova explosions. These are cataclysmic events that signal the death of a star, where it explodes. And what we have is that we have a star that had finished its cycle. It has a lot of iron, and then you have a cataclysmic explosion. So if you remember, I mentioned before, that's the nuclear landscape. So you can imagine here the number of protons going up this way, the neutrons going this way, and the black circles are the stable nuclei, the stable elements that we have here on Earth. And I'll show you a video of a simulation of what people think, or one of the scenarios that we have for how to create these elements. I want to point out that this is the time after the explosion. So this is immediately, not even 1 second after the explosion. You will see as I press play that there is a lot of nuclei that are populated in these white squares. And these white squares, these are all exotic nuclei. And depending on how, look, this is 10 to the minus 3 seconds. You see how many exotic nuclei we start creating through different nuclear reactions that are taking place inside this cloud of projectiles that come out of this supernova explosion. And you see how far away from the stability line we have gone. And depending on the properties of these very exotic nuclei, the abundances of what we think we are creating would look very different. So it's very important to look at these exotic nuclei. And you see now how it cools down. Now we are at 5 seconds after the explosion, and everything comes back to an equilibrium, and that's how we are creating the stable elements, that then they are ejected into the interstellar medium, and then you have life created through new planets and life as we know it. This is how the elements came to Earth. This is cosmic alchemy that you see there. Nuclei changing in milliseconds. So how do we study not just exotic nuclei in general, but even more so exotic, because I mean, they live for so long, so we don't know. We have only a few milliseconds to study them in the laboratory. So of course, if you want to study something big, you take your flashlight, you shine light on it, you try to observe, investigate how it looks like. If you want to look at something smaller, of course, you will go to your microscope, you look at smaller objects, and then depending on the scale that you want to observe, we can even go to the atomic level with very sophisticated routines. This is the electron microscope. But again, if you remember, this is the distance that we are 5 orders of magnitude away from the atomic nucleus. So electron microscopy won't work to look at the atomic nucleus. So what do? We need to find a different probe. And this probe is atom smashers. So what do? We go to facilities around the world where they can actually create these exotic nuclei that live for for milliseconds. And then we are trying to study them by seeing how they interact with a different nucleus. So we smash them together, different nuclei, and then we observe what kind of reactions or energy or particles are emitted through these reactions. And we can infer or we can observe properties of these exotic nuclei. So I have here the world map, and I want to highlight, of course, that these are very few facilities that can do this kind of experiments. In Japan, we have a few in Europe and in North America, but I want to take this opportunity and say that research students that are working into this field of nuclear physics or exotic nuclei, they are very privileged because they can travel around the world to perform their experiments, and they can experience different cultures. They can have nice dinners in Japan, or they can have this fantastic view of Vancouver, or this is downtown Chicago with beautiful architecture. This is my student Michael, very happy to visit downtown Chicago. And then if we go to these laboratories, again, how do we create exotic nuclei? We have here on Earth only materials, atoms that are not radioactive, right? They are not exotic. And that's the only material we can start with. We can start to accelerate this material through, for example, cyclotrons. This is a person, just to give you a feeling of the scale. And we can use special ovens. It's not an oven, but it's sort of an oven where you put, let's say, carbon in there, and you're trying to get to ionize it and then start accelerate these atoms. And I'll play this video where what we do is that we accelerate the stable species through our first cyclotron, then we give more energy, and I'm talking here about velocities of the order of 60% the speed of light, and then we place some material on the way, and these are atomic nuclei of this material, and what we are waiting is for a nuclear reaction to take place. And when a nuclear reaction takes place, then I create all sorts of things, and I'm using big magnets in order to choose the species that I want to study. This is very rare to make. I'm gonna play this video again, but I'm gonna talk on top of that. So it's very rare to make an exotic nucleus. Maybe once per million reactions will create one of the nuclei that we want to study, but we will pick out this event, and we will use these big magnets, and we will select it, and then we will redirect this into an experimental hall where the experiment will take place. Again, it would be a nuclear reaction, but now we have specialized equipment around the nuclear reaction point in order to see what comes out. And because it runs, the speed here that we are using is 60–70% the speed of light. Even though they live for milliseconds, that's enough time for us to perform the experiment, to deliver it to the experimental hall and also perform the experiment. So examples of what we want to measure, I'm talking about properties of exotic nuclei, but let me give you some examples of what it is that we want to measure. One of the most basic things that you can measure, it's the nuclear mass. That's a very important property of nuclei in general, and I believe Charles will talk a little bit more about this later on. What I want to highlight, of course, is that if you look at the masses, the nucleus will be lighter than the constituents, protons and neutrons. And there are many different techniques to measure a nuclear mass. I'm not an expert on this, but I'm always fascinated with this fact that they have progressed and advanced so much these techniques, that the accuracy that they can measure a nuclear mass is equal to, if you have a Boeing 747, a jumbo jet, they would be able to tell you whether you have added or removed a 1 pound coin from the plane. This is the accuracy with which we can measure nuclear masses today. Other properties that we can measure are excited nuclear states. What is an excited nuclear state? It's not the same as when, for example, you want to go to a party. That's not the excitement. Or when I give my kids ice cream. That's not the excited states that we are talking about. To understand or to give you a feeling of what exciting nuclear state is, I want to make the following analogy. Let's think of potential energy. And with potential energy here, you know, in our macroscopic world, you would just go on this leaf table, and then imagine that for every different position that you can take, it's like the potential energy, then you would have a different excited state. Now, atomic nuclei live in the quantum world, and in the quantum world, this does not work. In the quantum world, we have very specific energy states that the nucleus can take. And the analogy that I want to give is like a ladder. So the nucleus can only sit on a different step of this ladder. And the important thing about atomic nuclei is that each atomic nucleus has a different ladder. So by looking at the ladder of each nucleus, we can learn a lot about its structure and how the protons and the neutrons interact among each other, and how these nuclear, the fundamental forces that I mentioned before, how is the interplay between them in order to see the atomic nuclei that we see today. So this is one very important measurement that we can make. The other thing that this is, you know, this is something that I really enjoy doing, and this is my specialty or expertise, is that not only I look at excited states, so I want to find out the steps of the ladder for some nuclei, I also want to know for how long they stay in each step before they go down on the ground. So again, it's a time thing. I will call it again lifetime. It's a statistical process. So it is, what is the average time that the nucleus will live, for example, in this step before it goes down. And this going down is releasing the extra energy that it has by emitting a photon, a gamma ray. So we have an excited nucleus, and then after some time, it emits a gamma, and then we have a nucleus in the ground state. So it's a relaxed nucleus. So how can we actually study these things? The typical lifetimes that we are talking about is of the order of 1 trillionth of a second. I say it again, 1 trillionth of a second. So you can imagine that we cannot use clocks because they wouldn't be able to measure this kind of time scales. So we need to find a different way to do this kind of measurements. And what we are doing is we are exploiting the Doppler effect. So the Doppler effect, I can leave Sheldon Cooper to explain what the Doppler effect is. And then I can also show you a more reasonable explanation, but he's right, scientifically.
I hate what Sheldon's supposed to be.
Oh, he's the Doppler effect.
Yes. It's the apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer.
Let's hear it once more.
It's the apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer.
So this is the Doppler effect, and indeed that's the Doppler effect. But let's now see a different explanation that we live in our everyday life. So this is an example of the Doppler effect for a moving sound source, which is that if the source of a sound is moving, then depending on whether where you are sitting with respect to this movement, then the wavelength will be different. And I want to just play this video here where a fire brigade is coming. I hope it's not loud. And listen to the sounds, how it will change. So now it's coming towards you. And the sound changed because your relative position to this sound of source changed. So this is the Doppler effect. And this is what we are doing, not with the sound, but with the gamma rays. But the gamma rays is a wave, it's an electromagnetic wave. So the Doppler effect is the same. So how do we do this? So we excite the nucleus through a nuclear reaction, and we let it sit in one of these steps of the ladder. And when that happens, the velocity of the nucleus is velocity 1, and that keeps traveling towards this direction. Through this motion, it starts changing the velocity because it's losing energy, because I have this inside the material. So the important thing is that I have a nucleus that is traveling this way, and after some time, which is related to the lifetime of this excited state, I will have a relaxed nucleus, and this relaxed nucleus will have velocity 2. So what I want to know is, I know velocity 1. If I knew velocity number 2, then I would infer the distance that this nucleus traveled, and therefore I would know for how long it lived before it decayed. So how can I find out velocity 2? When the nucleus de-excites, it emits gamma rays. So what I need to do is to observe these gamma rays from different angles. And then, due to the Doppler effect, I can tell what is the velocity 2, because it's different, the energy of the gamma ray as it is observed from different angles. And that's how we can find out about the lifetime of excited states, which is of the order of a trillionth of a second, but we can do it very nicely with very high precision. Now, of course, we don't look at it by eye. This is only a cartoon that I make here. How can we do these things? We need to use very sensitive equipment. And I give you here an example of gamma sphere. This is gamma sphere. This is a 14-ton instrument. It's the world's most sensitive gamma ray microscope. At the moment, it lives in Chicago at Argonne National Laboratory. This is to give you the feeling of the scale. This is me, this is Michael, that's the happy face in downtown Chicago. And this is half of gamma sphere. So it's the sphere opened. And just to give you a feeling of how big it is, this is us in front of it. Gamma sphere, actually, you might not know, but it had featured in the movie The Hulk in 2003, that you see that Hulk was actually blaming gamma sphere for what happened to him, which is not true, of course. And the plot is pure fiction, but gamma sphere was real, or a mock-up of gamma sphere. And thank you for your attention.
Thank you very much, Marina. So with that, I'd like to ask you a couple of questions from the audience. Firstly, just a bit about lifetime. So many are familiar with the term half-life, but not so much about lifetime. Could you tell a bit about what's the difference between lifetime and half-life?
It's the same thing, only that the half-life, it's when your sample has decayed into the half of the initial one, and the lifetime you have a factor of a natural logarithm of 2. It's just a mathematical one, but the idea is the same.
Okay, thank you. So one thing that was really striking to quite a few about your plot of the different lifetimes for beryllium is that when you look at beryllium-7, it has a relatively long lifetime, whereas all of the surrounding isotopes of beryllium have lifetimes that are 10 to the minus 20 or so seconds.
Yes.
So why are they so different?
So it depends. For example, everything that is titled or mentioned as 10 to the minus 20, that means they don't make a nucleus. And then that's the scale of the nuclear force. So when you see 10 to the minus 20, that's not, you cannot make a sound system out of that. Even if you bring them together, they don't want to be together. So that's not an atomic nucleus. You cannot make a nucleus out of that. And then the rest, whether you will have a millisecond, a second, or so on, it really has to do with, for example, the further away you go, and the more neutrons you add, the system cannot live. It's not energetically feasible for the system to live. So the further away you go, the shorter and shorter the lifetime will be. But of course, there are other subtle effects. For example, in carbon dating, why does it live for so long? And we can do carbon dating. And I think Charles will touch upon that. So these are intricacies of the beta decay, for example, that until now we cannot explain. So it's very, very interesting.
Okay, so basically that the isotopes just around, effectively you can say that they almost don't exist because they fall apart immediately when you make them. Okay, thank you so much. That's great. And so just to be clear, that so actually Charles will not talk specifically about carbon-14, but actually there is some more.
Somewhere in the sorry. Yes.
That's okay, but there's actually much more information about this also on the course website. So another really interesting question is about how you make these. So how do you actually add neutrons to an isotope? How do you make these really neutron-rich beryllium isotopes with a lot of neutrons on them? And even more so, is there a limit to how many you can add as well?
Yes, so how you make them is that typically you would start with a nucleus that is much heavier, stable nucleus, let's say calcium. Calcium, you can go, you can have 28 neutrons and 20 protons, which is calcium, and that's a stable nucleus. So if you put in this oven that I was describing in your big accelerator, if you start with calcium 48 and you smash calcium 48, you can make everything that has less protons and neutrons. And because beryllium is so much lighter, you are gonna make all this exotic beryllium. The probability will be very small, but you will make them. And then you will use your magnets to actually tune and select this very exotic guy. And the question of how many neutrons you can add to your system, this is a contemporary question. We still don't know. We have calculations, we have theories, but each one might be off by 1 or 2 isotopes, or even 3 or 4. And it is exactly these isotopes that will define the abundances in the solar system. So we really need to know how many. In the lighter systems, we can see them experimentally because we can reach experimentally this in the laboratories. But if you go to heavier nuclei, we have no idea. It's very fascinating.
Okay, well, thank you so much for that, Marina. That is indeed fascinating to hear about. For the audience, we will actually dive more into the astrophysics of that already next week. So thank you so much for sharing that with us.
You're welcome. Thank you for
thank you for coming today. We might come back to you later on if there are more questions on these topics, and if we have time after Charles's presentation. So with that, I'd like to move on to Charles Barton to invite you on. So Charles is a lecturer also in nuclear physics in York. So welcome, Charles. So Charles is, in a moment, is going to talk to us explain a bit about binding energy and what that is, what is nuclear energy fundamentally. Charles also does research in nuclear physics, in part researches how nuclear shapes also affect the energy of nuclei. It's not specifically what Charles will talk about today. Charles will introduce us to some other concepts that we will need quite a lot over the coming weeks of this course. But before we get started, just one question for you, perhaps, Charles. What do you think is most surprising to you in the area of nuclear physics? Or most interesting?
Yes, so what I found most surprising in nuclear physics is just the complexity. You have 2 different kinds of particles. They're in the atomic nucleus. You've got protons and neutrons. They interact with each other, but relativity plays a factor in there. The charge does. It's a quantum system, so it's quite intricate how it works together. And you can form very simple intuitive models that explain aspects of the nuclear force. And you can have very complicated mathematical models, like a six-dimensional group theoretical approach, for example, does a fairly good job of explaining nuclear shapes and understanding that. And that's what I found so surprising, is just the multifaceted approach that this tiny quantum system of particles explores a whole variety of different phenomenon that are it's just fascinating to investigate.
Okay, thanks. That's great to hear, Charles. So I just wanted to hear a bit sort of your sort of personal view of it before you got started. But I think I'll just let you go straight into it, and thank you so much for giving us an introduction, a basic introduction to some of the concepts of nuclear energy.
Oh, yep, no problem. Actually, it's a little bit of an introduction just to energy, just to refresh our minds on what an energy scale is, because in science we use the SI units, for example, the standard international units, and so the unit for energy is usually joule, and joules are a bit challenging maybe to try to understand conceptually. So a joule, for example, I happen to have some props. So I have a liter of water. That's about a kilogram. And so if I needed to lift this, for example, I could talk about energy as potential energy, just lifting it against gravity. And so if I use my little ruler, and if I were to lift it by about 10 centimeters, and that's about here. So I've lifted it 0.1 meters. So we have mgh for potential energy. So mass is 1 kilogram. G is about 10 meters per second squared. And then if I multiply that by 0.1 meters, this is about a joule of potential energy. If I were to release it, it would have, when it hit my tabletop, 1 joule of kinetic energy. Ooh, there we go. And so there's that. Within our body, a single heartbeat to circulate blood and bring oxygenated blood to parts of the body, a single heartbeat is also about a joule of energy. And of course, we eat food. We use a lot of energy in the day. When I moved to the UK, I became introduced to dairy milk bars, which are very good. And if you look in the back of a typical dairy milk bar, you can see how much energy they have in joules. And in a single candy bar, remember, a heartbeat is 1 joule, or lifting that liter of water, 10 centimeters is about a joule of energy. This has a surprising amount of energy in it. It's got 1 million joules, 10 to the 6 joules in scientific notation, and 1 followed by 6 zeros. So you've got 1 million joules of energy that can be released here in the candy bar through a chemical process as you digest it and use that energy. Of course, I need several of these a day, but just this 1 candy bar, if I was to enjoy that, it could keep my heart beating for about a week and a half. So it's an incredible amount of energy. Of course, candy bars have gotten a bit smaller over time. About 2 of these would give you about 100 grams. So you'd need 20 candy bars to give you 1 kilogram. And so 20 candy bars, 1 kilogram of candy bars, would be 20 million joules of energy. And that's almost enough to keep my heart beating for a year, a good fraction of a year, for example. And when we look at some of the exercises, we'll be looking at other aspects of energy scale. For example, if we wanted to understand how much energy is released or used, for example, by me, a typical person here in the UK, I'd use about 20 billion joules of energy from the national grid a year. That's 20 or 2 times 10 to the 10 joules of energy per person per year. So if we go back to our candy bar scale, we're now talking about, pardon me, 20,000 candy bars worth of energy in order to generate the electricity that I would need per year. And then we could also just talk about 1 kilogram of water. Einstein's equation, E equals mc squared. Well, the speed of light, so you've got 1 kilogram here. you've got the speed of light, which is 3 times 10 to the 8. You square that, you get 9. 10 to the 8 squared, you multiply the 8 by 2. So you get 9, 10 to the 16 joules. That's about 10 to the 17 joules worth of energy released if I could convert all of the mass of 1 kilogram into energy, for example, just pure energy using Einstein's equation. That brings into account energy for the nucleus. And what I'm particularly keen on just exploring is one of the simplest nuclei around. You can have a proton, and I have just another prop, a single proton, let's say. Okay, and so this proton, it's not very exciting. For the nuclear force, you need at least one other nucleus, and we'll be exploring this. So to understand the nuclear force, let's bring a neutron into play. Okay, the neutron in my prop here is a little bit bigger. The surprising thing is the proton has charge, the neutron does not. But the neutron's actually heavier than the proton. And in physics, or any system, nature wants to be in the lowest energy state. Following the Big Bang, as things were very hot, just seconds after the Big Bang, you began to cool down and create things like protons and neutrons. And they were created in equal numbers. But nature would look at this and say, the neutron is heavier than the proton. It should be able to decay and become a proton. And that's exactly what neutrons began to do in the early universe. Within the first couple of minutes, neutrons were decaying away. They started out in equal numbers, but after just a couple of minutes, the ratio was about 1 neutron for every 5 protons. And it decayed even more. Today in the universe, we only have 1 neutron for every 7 protons. And that's very peculiar, but that aspect of the nuclear force tells us a great deal about the early universe and dictated the evolution of the universe. So the tiny nucleus can influence the entire universe and its constituent components, not just all the elements, just even single nucleons began to do that. But of course, the neutron, it decays away over a matter of minutes. If I had a bucket of neutrons and came back tomorrow, it would decay to be quite a few protons in there and very, very few neutrons. The neutron is stable inside the atomic nucleus. So that gave us the scale in the early universe of when nuclei began to form. And so how does that work? The interesting thing is if I've got a proton and a neutron, they have a certain amount of energy, for example, in the early universe. So let's just, try to balance it on this little platform. As they get close together, they formed their own binding energy. And here's where I'm going to try to explain what happens here. The free proton and the free neutron get close enough that when they come basically into contact, they form their own potential and they're bound. The binding energy can be thought of as the energy that you would need to put in and take the nucleus apart. But that's not just for nucleus, any binding energy in atomic physics, in chemistry, how tightly is an electron bound to the system? It's the same principle. The potential is different for an electron in an atom. It's in the Coulomb force. But here, the nuclear force makes its own potential and drops it in. The interesting thing now, I've got this model of deuterium stuck in the glass. And so it's stable, but it's a bit more subtle than that. And as you'll look for deuterium and looking at the nuclear chart, just building upon adding protons and neutrons together, there are aspects that might be quite fascinating to you. And so if we look at this simple bottle of deuterium, we can say, well, that's nice. I'm forming an intuitive picture of the binding energy here. But deuterium is quite fascinating. One of the things that will happen is this is a quantum system. You can't have zero energy. And so as you constrain the space, and a proton and neutron making deuterium is nature's perfect example of a quantum dot. Basically, they create a quantum dot. Just they're constraining themselves in space, but as you constrain space, the momentum becomes worse defined from the Heisenberg uncertainty principle. And so the proton and neutron don't sit at the bottom of my model glass of the nuclear binding energy. Instead, come to find out that model glass would be like 35 million electron volts deep. Okay, an electron volt is another unit of energy. It's the energy a single electron gets if it goes through 1 volt of potential charge. We may know from hydrogen, the electron bound in there, you're bound at about 13 electron volts of energy. Nuclei, they're 100,000, a million times smaller. The energy is 100,000, a million times higher. And so now we're talking about millions of electron volts of energy. And so a proton and neutron creates a potential well, this empty glass that I was talking about, that's 35 million electron volts deep. But the ground state of deuterium is right at the very top of the glass. It's only about 1/20th, at 5% of that level. The binding energy for a proton and a neutron is not the full well depth. It's where the ground state, the lowest energy state of your quantum system is. And that's at just 2.2 million electron volts below zero, where we measure things from, where things become unbound. So deuterium, it looks like the nuclear force is strong. We talked about the weak nuclear force that would decay a proton in, a neutron into a proton, or vice versa in some situations. But here we've got the strong nuclear force that's binding and making the nucleus stable. We think of the strong nuclear force, but in the case of deuterium, it's very weakly bound. How weakly bound? The interesting thing about deuterium is not only is it a perfect quantum dot, but because it's so weakly bound in the early universe, that gave us a parameter to explore how strongly dark matter interacts with normal matter. What's dark matter? Nobody knows, which is why we came up with the imaginative name dark matter. But if it interacted strongly with normal matter, the belief is that dark matter is 10 times as abundant, for example, as normal matter. If it interacted strongly with deuterium, it would just have broken deuterium apart, and we'd have a very different amount of deuterium in the universe than we have today. So this puts an upper limit on some fundamental things that we don't know what it is, but we need to better understand. And the hope is that the generation who are listening to me now can explore some of these fundamental properties of the universe and the physics that we don't understand, and push back those frontiers of human knowledge. So we've got deuterium barely bound, and it's even more fundamental than this, because you can ask yourself, well, wait a minute, can any 2 nucleons get bound? Well, if you have 2 protons, no, and that's somewhat sensible, because you'd say, well, the charge is so strong, when you squeeze 2 charges together, they'll repel. Okay, so that's sensible. How about 2 neutrons? No, there's no stable 2 neutron or 3 neutron or 5 neutron matter anywhere. The only stable neutron matter that we believe exists in the universe are neutron stars. And that's because you get so many neutrons in one place that the extra gravity gives you the enhanced stability that you need to give you pure neutron matter in some sense. But a proton and a neutron is different than 2 neutrons and 2 protons. It gives you an added bit of binding energy, but not for every orientation. Quantum particles often have an inherent property, spin, some kind of angular momentum. You can think of them as spinning like a top. And if we look, the neutron could be spinning with the right-hand rule so that it's spin up. The proton would also have spin up. This is the only configuration. The ground state has to have spin up. If you flipped one of these spins upside down, deuterium falls apart. There is no excited state in deuterium. And this is explaining why it's such a perfect quantum dot, which for quantum information and quantum communications and things like that, quantum dots, quantum computers and so on, it's quite an interesting field. And a lot of people are trying to create such things. Nature's done it with deuterium here. And so we have this very simple part. And so there's quite a bit of physics in deuterium that manifests aspects of the nuclear force. Now I've mentioned binding energy. Mass excess is the reverse of that. So binding energy, you can look at in deuterium. The mass of deuterium is almost entirely made up of the mass of the particles. The binding energy is just a very tiny amount of the system, but that affects the overall measured mass of deuterium. So there's a mass excess. Protons and neutrons would give you deuterium and release some energy. They have excess mass. It's like the inverse of binding energy. If we understood everything about the nuclear force, we could predict the binding energy, but we don't understand the nuclear force well. So many people look at binding energies and masses and try to extract nuclear force information. What is it about the strong nuclear force and its components that we don't understand? And that's essentially where our research is looking at. We have very simple models trying to build up simple intuition, but those models don't explain all aspects. And as you probe deeper and deeper into nuclear physics, as with many fields of science, you just uncover just fascinating extensions and amazing topics. And that's one of the other things that I like about any science research is that people get together. They're very passionate about this. They find it very interesting. They work very hard trying to understand it. But you need to develop your intuition as well so that you can better understand how the world around us works. I'm aware of the time, and I thank you for listening. And
thank you very much. Yeah, thank you very much, Charles. Just there are plenty of questions from the audience, but we can take just one or two. I wanted to ask you, based on some of the questions, so are there any cases in the universe where not only neutrons would decay to protons, but also the opposite, where protons would decay to neutrons?
Yes. In fact, you can think in some nuclei, you have a potential well where both protons and neutrons sit, but the neutrons don't have charge while the protons do. And basically, your energy for protons and neutrons, the wells are a little bit different. And much like you can create an isotope where you put more neutrons in and more neutrons in and more neutrons in until you physically can't put any more neutrons in, it's very neutron rich and it would decay. You can have an example where perhaps it's proton rich or neutron deficient, where the imbalance is so extreme that the protons will decay. And that gives you, for example, if a proton decays into a neutron, you lose a positive charge. Nature and physicists seem to like to look for conservation things. You've got to conserve that charge. So now you emit a positive electron, a positron from that kind of decay. Whereas a neutron, if it decays into a proton, it goes from zero charge to a positive charge. So it has to emit a negative electron to conserve charge. But then, of course, an electron is very different than a proton. So now you have to consider a neutrino in order to conserve what's called lepton number. Lepton's the family of particles that are electron-like.
Okay.
Yes.
Yeah. Okay. Well, thank you so much, Charles, and also thanks to you, Marina, for joining us, and thank you to all of you for listening into this, and for those of you who'll be watching this later in the week when it goes live. So I just wanted to point out a couple of things from what has been covered today, that this aspect about energy and the different types of decays, beta decays, plus and minus, neutron decay, proton decay, all of those decay types and types of energy are covered in much more detail on the website and through the videos that are embedded on our site, as well as through some of the quizzes and questions and questionnaires that we have embedded into the website. So I would encourage you to work your way through that during the week, ask questions on our online forum. If you didn't get an answer to some of the questions you had today, which I've seen, we've got plenty of questions coming in, please do ask them again also on the forum. There will be experts available to answer your questions during the day, during the slots particularly that you've been told about, late morning and this time in the afternoon throughout the week. So with that, thank you so much for tuning in, and we'll be in touch during the week, but we will see you in the same slot next week. Thank you.